by Lida Oskinova about high resolution X-ray spectroscopy. And she's going to give us a review talk about the shocking truths about massive stars.
Thank you very much for giving me a possibility to talk, to give this remote talk, and I very much regret I cannot be with you in person. So my talk is about stars which start their life with initial masses above 8 solar masses, and they are going through various evolutionary stages before exploding a supernova or gamma ray burst or anyhow undergoing a core collapse event. The key point that stars which start as massive as above 8 solar and then become a neutron star or a black hole, as shown on this picture. This is accreting neutron star in a high mass X-ray binary. And now we are living through renaissance of massive star studies because, of course, discoveries of gravitational wave astrophysics, which discovers a multitude of black holes with stellar masses. And one of the predominant channels for production of these binary black holes, which merge with gravitational wave events, is going through massive star evolution. So to understand, to have the full significance or astrophysical significance of gravitational wave detections, the focus is on massive stars studies. And one of the key features of massive stars is that they have prodigious strong stellar winds, which are driven by the UV radiation of their central star. And by rule of thumb, a star could lose up to 1 solar mass per year, 1 solar mass per million years, and with these short lifetimes, mass loss rate is very significant. Therefore, one can easily imagine to get those heavy black holes like absorbing gravitational waves, it's better to have weaker winds. And since wind strength depends on metallicity, all the slow metallicity environments are now receiving a lot of attention. So stars are losing a lot of mass during their lifetimes, and stellar winds are predominant mechanism of mass loss, at least what we are thinking by now. But mass loss rates from massive stars are not very well known, or rather unknown, and dependence on metallicity is also not exactly clear. What we know about massive star winds, however, is that they are multi-phase media. And this is known because all stars which are earlier than B2, roughly B2 spectral type, they emit X-rays. And the thinking already since many decades is that hot plasma emitting X-rays is permitted with cooler plasma. So cooler plasma has temperature about 10,000 Kelvin. Hot gas has about 1 million Kelvin, and they kind of dynamically couple and coexist with each other. And another key point to keep in mind that the stellar winds are clumped. So they are not homogeneous, and the density structures, both small and large density structures. So now we have access, like we just talked, we have access to high resolution X-ray spectroscopy since a few decades now, and this provides us exclusive information to the hot part of stellar winds, which we can put in the context of the whole understanding of stellar winds, which is much needed to understand stellar evolution towards the black holes and compact stars. So before continuing, I would like to make a couple of remarks about key diagnostics, which we have from high resolution spectroscopy. Of course, you all there experts, but know much better than myself about all the stuff. But I would just like to remark on a couple of things. So as we already heard today, the shape of X-ray emission line profiles provides valuable information about absorbing column in stellar winds. And this is then matter of interpretation how this information could be used to derive mass loss rates or other properties of stellar winds. So another interesting point, which is different from other branches of X-ray astrophysics, is helium-like ions and associated diagnostics. As we also heard this morning, helium-like ions, the low flux and forbidden line is typically interpreted as because of low densities. While in our situation, when central stars are very UV bright, so the absence of forbidden line is predominantly because of depopulation of metastable level because of UV pumping to the intercombination level. So furthermore, interesting point that when we are dealing, as I mentioned, stellar winds are multi-phase media. Therefore, actually, the advanced model tried to model together from first principles both X-ray spectra and UV and optical spectra together. This to have access to the full range of electromagnetic spectrum. This is, of course, a very sophisticated and very advanced attempt to understand the structure and properties of stellar wind, and so far not many works done in this direction, but maybe in the future. Okay, I will finish with introduction now, and now I would invite you to sit back and relax and take a guided tour in the upper part of the Hertzsprung-Russell diagram and look through high resolution X-ray windows left and right of the main sequence. We will make stops. So you see here, this Hertzsprung-Russell diagram shows quite generic stellar evolutionary track of single 40 solar mass star. And we will make stops in these different parts of a massive star life, from main sequence to cooler part of HRD and then to hotter part of the HRD. So our first stop is main sequence OB stars and the weak wind problem. So majority of OB stars are late stars on the main sequence, so late spectral types. This is, of course, simply because of the initial mass function. So majority later stars are more common than earlier type stars. So therefore, OB dwarfs, in fact, is the most common type of massive stars, and they are predominant suppliers of neutron stars in the universe. So, and then the stars have a problem. So wind mass loss from the stars, which measured from optical and UV spectra, is 100 or 1,000 times smaller than theoretically expected. So now what to do about it? Who is wrong? Theory is wrong. Observations are somehow systematically misinterpreted. So what is the problem? And this is acute problem, which is called in our business, it is called weak wind problem. It was noticed already quite early from 90s from Rosette observations that X-rays might play a role, because before advance of grating spectroscopy from low resolution spectra, just from fluxes, it was clear that emission measure, which measured from the stars, from fluxes in X-rays, significantly higher than emission measure of wind, which we observe in optical and UV. Yeah, so you should always keep in mind that it's multi-phase media. So in optical and UV, we measure flux coming from cooler part of the wind, so the cooler clumps, and X-rays we measure what is happening in the hotter part of the winds, in hot part of the wind. So, and with this discoveries made in the 90s, two possibilities were open. Do X-rays destroy stellar wind? So stellar winds are indeed very, very weak, or the winds are hot. So, and the bulk of mass is present in this hot phase of stellar wind. So Chandra and XMM Newton invested quite a time observing this, what we call weak wind stars, to try to understand what is the answer to this problem. And here I show one of the spectra of, so Chandra spectrum of O-type late O-type dwarf, which is called mu Col. And so we use this high resolution Chandra spectrum to understand using helium-like diagnostics to establish basically geometry of distribution of a topology of hot plasma, hot X-ray emitting plasma, and we used the shape of the X-ray emission lines to determine the velocities, how velocity of hot plasma, and understand its dynamics. So, and combining this also topology and dynamics give us, we hope, give us answer to the question. So we established that mass loss rate, which we measure from X-rays, it's order of magnitude higher than mass loss rates, which is measurable from the UV spectra. And moreover, the velocity of hot wind exceeds velocity of the cooler fraction of the wind. And approximately at the same time, it was also some theoretical works on this topic. And now what community think is happening in wind stars is that the wind is clumped, and clumps contain only a smaller fraction of the wind mass. And majority of the mass in O-type stars, this type of, dwarf O-type stars, is in the hot phase and consequently is observable only in X-rays. And in my view, it makes a huge value of grading resolution of O-type dwarfs, because it's provide us to access to the beginning of life of neutron star progenitors. Okay, so that was this part. I hope you can see my cursor mouse. So this was our first stop on the main sequence. And now we are starting to move slightly off the main sequence and arrive to the blue supergiant stars. And they are strong wind problems, because these stars have mass loss rates which are thousands and maybe 10,000 of time stronger than O-type stars on the main sequence. So supergiants are super interesting objects. They have strong and often CNO enhanced winds, and it immediately says that these winds are very good in absorbing X-rays. These winds are also strongly clumped. And UV and optical wind diagnostics are affected by clumping, and in massive star business, and now also in gravitational wave astronomy, astrophysical applications of it. It's a lot of talking about clumping. And it was noticed already by Stewart and Fabian in 1981 that X-ray transfer of X-rays through a wind is a useful tool to estimate wind density. Now, recently, grading spectroscopy of high mass X-ray binaries telling us something about structure of donor winds. So high mass X-ray binaries is typically consist of blue supergiant and a neutron star or a black hole, which accretes wind lost by a donor star. And neutron star or a black hole is basically a point source embedded in the wind of the supergiant, and provides a very useful diagnostic tool to study wind structure. So what we learned from work of colleagues here, Victoria Greenberg and her group, and I cite here a couple of papers. So this is a spectra of Cygnus X1, which change with time, and the interpretation of the various dips, which are seen in the spectra as time progressing, as the line of sight passing through various clumps in stellar wind, and these clumps are having structure, could be studied, and they are optically thin for X-rays, and their size and parameters could be estimated. So this is another work also with a similar objective to understand the formation of clumping in stellar wind, and using in this case, neutron star, to probe the wind density and how close to the stellar photosphere clumping originates. So with this, I must mention, and I'm sure we will hear talks later on today about the largest time investment Chandra did to study supergiant stars. This is a very large program aimed at Zeta Puppis, and it is the best X-ray spectrum of an O star up to date. And there's a number of papers, which of course it's a fantastic data set, which devoted to the analysis of this data set. For instance, it was established that the maximum temperature in stellar wind of this star and similar objects is about 12 million Kelvin, and this temperature is achieved already quite weak in the wind. I didn't mention that grating spectra great for doing abundances, and of course here the part which is shown on this from this paper by Hunimerde and colleagues shows fantastic spectroscopy of metal lines, which, by the way, is very important for understanding evolutionary status of the stars. So the next chapter, in my view, is simultaneous observations of the next chapter, in my view, is time monitoring of variability in O-type stars. So what came perhaps quite unexpected in the last, say, 15 years or something, is that X-ray show variability from O-type stars, and this variability changes on time scale of rotation. So the plot here shows, I hope you also hear in other talks today about this plot of Zeta Puppis, which shows that variability in X-rays is faced with variability in optical. And the interpretation is that somehow there are spots on stellar surface and variability in optical because of rotating spots, and variability in X-rays, it also reflects somehow this situation. So there is another star, Lambda Cephei. Actually, to the best of my knowledge, for deep enough observations of O-type stars, they always show variability of a few tenths of percent, so about 10% on rotational time scale. So what we are doing now, this is really the cutting edge observations from my point of view, is that we are doing simultaneous observations in optical and in X-rays. Sorry, in UV, optical, and X-rays. And this is very much needed because, remember, winds are multi-phase media. So when we observe them together, we can see dynamics and how hot part of plasma emitting X-rays interacts with cooler part of the plasma, which emits in this case in UV when we do UV observations with Hubble Space Telescopes, or in optical when we study, for instance, H-alpha. So with UV, we did 2 campaigns on 2 stars, Zeta Persei and Zeta Ophiuchi, with different spectral types, and this is coordinated, attempted strictly simultaneous observations with Hubble Space Telescope and XMM, and trust me that simultaneous observations with space missions are very sophisticated. So what did we learn? Indeed, we learned that X-ray variability and UV variability are correlated, and things are changing on similar time scales. So perhaps it is not surprising because, yeah, the winds consist of hot interclump medium and cool clumps, and somehow they interact, so where's big surprise. However, the surprise comes from the time scale. This time scale for variability is time scale of days, not dynamic time scale of the wind, which is hours. So this is surprise. And this is interesting plot, I think, which shows the oxygen and light, oxygen 8 line, difference between dwarf star. So the black line is dwarf star, which basically show no wind absorption, and the red line is O-type giant, whereas line is shifted, indicating that there is wind absorption. So what is the current ideas about why there's coordinated variability in the UV and in X-rays? And so let's go from left to right. So the left picture is just a cartoon which shows a subsurface convection zone in massive stars. So this is advent of the, say, last 10 years, when it's from theoretical and from numerical modeling point of view. It is now, we believe that there's in massive stars, subphotospheric convection zones exists. And this convective zone could penetrate and break magnetic field lines on the top of stellar photosphere. And there, where the processes associated with generation of hot plasma and maybe production of clumping take place. So the next picture in the middle is basically the same idea, but it is now full 3D radiative magnetic hydrodynamic simulations, which shows that under stellar surface magnetic lines are entangled and then they go vertically up through stellar surface. So perhaps this somehow connects together stellar spots, clumps, rotating interaction regions, which give the rays of these variations on the rotational time scale. Okay, my time is running out. So now we are moving to the coolest tip, to the luminous blue variables and hypergiant stars. So, and they are X-ray dark unless in a colliding wind binary. So, of course, the most famous example, no talk about massive stars, could go without mentioning Eta Carina, and here it is. So this is high resolution X-ray spectra of Eta Carina at different phases, which shows hugely different spectra. And very briefly, it's huge literature on the subject. These observations were absolutely paramount in understanding the physics, what is happening in this one of the most important stars to study, the most massive stars in our galaxy. So my next stop, we change from the coolest part of this track to the hottest part of this track to Wolf-Rayet stars. And this will be a very short stop for the reason that so far the only one spectrum, high resolution spectrum of only one Wolf-Rayet star exists. So the closest Wolf-Rayet star, single Wolf-Rayet star is called Wolf-Rayet 6. And both Chandra and XMM observed the star, and no other single Wolf-Rayet stars were observed with gratings up to now. As far as I know, please correct me if I'm wrong. So what did we learn from the unique Chandra high-resolution observations of Wolf-Rayet stars? This is this Wolf-Rayet star, this what we call the Finn type line profile, very, very skewed. So the X-rays are strongly absorbed in stellar wind. A and B, their spectra of helium-like ions show prominent forbidden line, which means that in this object, at least, X-rays are formed very far from stellar core. How X-rays produced in Wolf-Rayet stars is not exactly known, except that they also show modulation with rotation. Okay, now the next stop is colliding wind binaries, and this is very, very short stop, because actually one should make the full conference about colliding wind binaries. Perhaps this is the best studied part of massive star X-ray astronomy with tons of data. I just, without citing papers, I cited just names from people who came into my mind who very actively work in this field. And there are many more. I'm sorry, maybe I I'm sure I dropped some names. But the key point here is that twins of two stars collide and produce X-rays and dust. So the picture here on the lower left corner shows the very recent GWST observations of a star which is called W140. This is WC star plus OB component. And you see these concentric circles, it's dust shells which the star emits. And this is X-ray spectra of W140 obtained with Chandra. what is very important and interesting about colliding twin binaries that the north thermal processes and maybe collisionless shocks are taking part in the systems. But I'm sorry for many people who work in this field. I have no time to talk about it. In our final very short stop is about strongly magnetic early type stars, and I believe we also will have talk about magnetic stars. Therefore, I just briefly mention it here that only 10% of stars have strong magnetic field, and the interaction of stellar winds with magnetic field leads to X-ray emission, and when studied at high resolution, it provides very important information about magnetosphere and dynamics of plasma in this wind. So, and I would like to conclude that decline of soft response in Chandra really hurting studies of massive stars and stellar wind, and that, in my view, the next step to better understand this object is time phase resolved spectroscopy, high resolution spectroscopy, and maybe coordinating observations. Thank you very much for your attention.
Thank you so much for your overview. Are there questions in the audience?
So is that mass loss problem solved?
No.
What new avenues of X-ray spectroscopy can help us probe that? Is there some, I mean, I heard you mention that you're primarily targeting single O stars, but because most are in binaries, is targeting O stars and binaries maybe the next step to go?
So, no, yes and no. So when we target this high resolution spectroscopy, massive stars and binaries, X-rays there are predominantly produced in winds colliding with each other. So how much we can learn from it about individual stellar winds is a good question. Maybe not so much. Maybe yes, but it is not obvious. So the X-rays are produced there by somewhat different process than in single stars. In single stars, in my opinion, the two avenues to go is time variability, so better data, longer data, coordinated observations with UV, and we need to go to other metallicities, because that's where this connections with gravitational waves and with other, not necessarily, I mean, I put emphasis on gravitational waves, but another very important emphasis, I guess, I think it will be tomorrow, is on high mass X-ray binaries and accreting neutron stars and black holes. And question of metallicity also comes there. So we need bigger, better Chandra now and XMM.
One last short question.
Okay, Linda, very nice review. Could you, Linda, kind of remind us of the heating mechanism for the hot wind, say from OB stars?
There is no short answer. So they are traditionally what we call standard model are linked with intrinsic instability of line-driven winds. This is their standard situation. However, in my view, in my personal opinion, new data challenge this model. I believe that their subphotospheric convection zones and spots and magnetic fields have play a role. So I think I'm not ready to answer to your question, and I think that yeah, the question is, in my view, remains open.
You mean the weak winds, the ones that are, let me see, hot wind, 2 million to 2 10.
About what is heating mechanism in weak wind stars? Yeah, the same. Who knows? So they could be, it could be line-driven instability. It could be subphotospheric, spots. So the very important thing happened. The spots are discovered on massive stars. They are seen in photometry because now, we have fantastic photometry because of planet searches. So spots are seen on massive stars, and where spots, there's magnetic field. Where's magnetic field? One can say there are X-rays, but it is all hand waving. So we are living in interesting times.
I was wondering whether the beneficiary connection is important.
I think we'll have to take that discussion to Slack so that we can continue with our next talk. Let's thank the speaker again while the next one puts up their screen.
Yeah, I'm very sorry I'm not among you guys. Thank you.
Sean Gunderson is our next speaker, and John, you should be able to share your screen now with us. We can see it, so please go ahead. If you're speaking, we can't hear you though. You need to unmute.
All right, can you? Perfect. All right, I want to continue this discussion about massive stars, or hot stars as some of us call them, by talking about how satellite lines can be used to probe the plasma conditions in the shocks from that are embedded within the wind. So the X-rays from the hot stars tend to come from, or are thought to come from, embedded shocks within the wind caused by differential acceleration on the clumps that make up the wind due to the line shadowing that occurs within them. You tend to get velocities about 1,000 kilometers a second in difference, so that corresponds to bulk kinetic energies thermalizing to about 1 keV in energy. You could do an entire talk for an hour on just this topic. So I want to instead go to the other end, to the X-ray generation, and ask, what is the plasma state in these shocks? Because that is an important question to determine what kind of physics we put into our models. And there's two I want to highlight in my talk. The first is the usual CIE approach, and the other is what I'm going to call Pollak's paradigm. So CIE, the collisional ionization equilibrium, is the standard assumption or approximation. It usually works. Astronomical timescales allow for equilibration to occur in a lot of shocks that we see, especially from like supernovae, and might occur in these winds. But then we can get some characteristics of, we see thermalization between species, and we have ionization occurring from ion-electron collision along with excitation. But that's not necessarily what's always going on, and there's always proposals of what else there could be. One of those was proposed by Andy Pollack in 2007, where he argued that the length scales are actually too long in the hot star wind shocks for ion-electron thermalization to occur before the hot gas from the shock quenches with surrounding cold gas. And he also argued that there's no thermal background in hot star spectra, so why would there be hot electrons? So really, a Pollak's paradigm type spectra should expect to see no hot electrons, and you would expect then the ionizations and excitations to occur from ion-ion collisions, which are much different in nature and would give you very unique spectra, we'll say. Now, to probe this, which is a really hard problem to do, I imagine we all know that you can't always test for CIE or the general plasma state. But in this case, there is a way to do that. And that's through satellite lines from dielectronic recombination. Now, these were talked about a little bit earlier today, but as a quick reminder, satellite lines are transitions in the parent J-state ion that are always at a lower energy than the resonance line because they come from a child ion at for J-1 state. As an example from some IXO simulations, you see the iron Lyman alpha lines that are resonance, and to their left at a slightly lower energy is a satellite line. Now, the dielectronic recombination process is really powerful in this way because All that matters is that you have a hot electron that's at a little too much energy hitting the parent ion. One electron is being absorbed and is promoting two of them to a highly unstable state. And that can either auto-ionize back out, or you can decay down to the ground state in the child ion and give you a satellite line. And this is really powerful because if we can compare the satellite line to the resonance line, we can actually use this to probe plasma conditions. So I'm going to call the satellite to resonance line ratio as just H for simplicity. And an example of this was done by Phillips et al. With the solar corona using RESIC data with silicon-13 helium beta and its associated satellite line, which I have highlighted right here. Now, in an isothermal case, you can write down a really nice formula for the temperature of the plasma based on this. And this has no assumptions of ionization state or densities because it's always the same parent ion and target. Silicon-13 in this case is what you're looking at, and it doesn't matter what's going on around it. It's only going to care about that. Now, for a hot star, though, we don't have this nice isothermal case as Lydia just talked about. Instead, we need to use a collection of temperatures, such as a differential emission measure, as was done for Zeta Pup with Hunemorter et al. In 2020. So in this case, we can't just make a nice exponential formula. Instead, we have to integrate the emissivities weighted by the differential emission measure. In this case, with the DEM that I'm using, which is the same one that Hunemorter et al. Used, was a power law with a max temperature of about 12 megakelvin and a slope of about 2.6, well, negative 2.6. And you can see on the plot on the right, which is a contour plot of what the ratio is at for different combinations of beta and T max, how the ratio will trend with these. So we can increase this line ratio by increasing the slope of the power law. So we're cutting off more of the high temperatures. Or if we just directly cut out the higher temperatures, we can also increase H. Now, there's a lot of reasons for this that I can't get into, but the resonance line is, the satellite line is much faster being affected by, or much more affected by higher temperatures. So this is kind of why this is occurring. Now, I didn't mention that we're going to actually use a test case for this on how to do this. And that's going to be with Zeta Pup and the deep exposure of these, of like 813 kiloseconds from cycle 19. Now, I'm showing the differential emission measure fit from Hunemorter et al. To highlight that there are two pairs of satellites that we can use for this analysis. These are the silicon-13 one mentioned previously, and you can directly see its satellite line in this figure. And the other is magnesium-11, and you can kind of see its satellite line right here. It's a little bit weaker. So to do this, all we need is the fluxes from those lines. For example, you can get those using a Gaussian model fitting, such as what I show on the left here for silicon-13. And you get something that seems wrong. That doesn't seem to match up between these two models. The magnesium-11 does match up reasonably well within 1 sigma error, but the silicon-13 doesn't. It's actually pretty far off, even at the lowest level or the lowest error for the Gaussian fitting. But that seems like a problem at first, but Hunemorter's fluxes that we got from his model are not actually direct measurements of the fluxes. They are a secondary model fit or a process you can get from it. So we're not actually directly measuring the flux with that. So to do a better comparison, we can calculate a predicted differential emission measure ratio using the integrals from before. And when we do that, the best fit parameters actually do predict the observed ratio from the Gaussian fitting. And because the Hunemorter differential emission measure model was built on CIE assumptions, this can actually be used as evidence for CIE because we have some very well-constrained line ratios that were found to be independently fit for their fluxes and found the right thing. More importantly, this is also evidence of hot electrons. If we use the isothermal case to give us a characteristic temperature of electrons involved in this process, we do find that they are quite hot. Comparing the temperature TE to the temperature of maximum emissivity from the APED in AtomDB, we find that the differential emission measure model does shift the peak emission to lower temperatures, but they are, again, still very hot. And this can tell us that CIE is relatively met and there's hot electrons. So this is a really powerful technique, and it's some very important conclusions. Because first of all, again, we have hot electrons, which means Pollak's paradigm is not the plasma state. And while that's not good for Pollak's initial theory, it's still interesting. We should explore how ion-ion collisions are occurring and maybe are affecting spectra, because maybe there's weird features that we can't really explain in CIE. But again, this is evidence of the post-shock plasma state being in CIE, so we don't have to go fix all of our old models and old papers. They all should still work. And then finally, satellite lines can be used for massive star wind analysis. These are relatively new to be done because we need a lot of data to see them. Again, for Zeta Pup, we needed 813 kiloseconds. So to do more of this, well, we're going to need something like Athena or Arcus, which just has a lot of collecting area to just get all the photons we need to see them. Thank you all, and I'll be happy to take your questions.
Are there any questions for Sean?
Yeah, just quick comment. There's actually more than 2 megaseconds of XMM time for Zeta Puppis. Of course, for the Silicon 12 satellite line, probably the resolution is not good enough. But I have a general question about these clumps in the All-Star winds. And sorry, that's not related to the satellite lines. It's more a general question about the All-Star winds. You know, when they're clumpy and these clumps are dense enough to produce sufficient X-ray emissions in isolated all-stars, I just wonder whether these clumps are also dense enough to produce absorption, of X-rays that should lead to variability in the X-ray light curves or features in the spectrum. I'm not in the field, so if the answer is no.
It's not quite thick enough to do that.
So, I mean, you need a density for the shocks, for the excess, so okay.
So what I'm saying is that after the shock, the clump obviously will expand. So the denser it is, the faster it's going to cool. But generally speaking, if you look at the opacity of the post-shock plasma, it isn't optically thick to X-rays.
Okay.
But overall, you're going to see those cooler clumps lead to a lot of photoelectric absorption. And that's what you see, for example, in Lida's and in Rico's talk. Do you want to comment?
No, just that the clumps aren't the hot component. They're the cool component by and large.
Yeah, exactly. Yeah, clumps are the cool component. And observations of high mass X-ray binaries, they directly show that clumps are optically thick for X-rays. Therefore, from, for instance, Cygnus X1 series of high resolution spectra show moving dips, which are attributed to moving clumps.
I have a quick question, I guess.
You can keep that for a second. We'll have the question by David Cohen first. He said, have you taken a look at lower mass loss rate stars? It seems like that's where you'd see more collisionless shocks. Sean, do you want to comment on that?
I've checked the archive for some of the lower mass loss massive stars, and you can't see these satellite lines in them. That there's just not enough observation time on them. Maybe I missed it, I will be honest there, but from what I saw, you just can't see them. There's not enough observation time to get the counts above the continuum.
Thank you. You had another.
It's actually quite related. I was going to ask, what's the next best case that you might apply this to?
As I think Zeta Ori it might have enough data for this. I think that has like close to 500 kiloseconds. Someone can correct me on that, like David Cohen can.
Thank you. Let's thank Sean again while our next speaker comes up.
Evening.
But before we get to the next speaker, I want to remind you that tomorrow we're going to have the Legacy of Chandra session, and I want you to put questions that we want to discuss, or up or downward questions. The link is also on the Slack, but most of you have computers open. It's onlinequestions.org, and our event is number 17644. 17644. There's currently a number of questions. You can add questions with new, or you can click on these things to upvote them. And then tomorrow the SOC will pick the top voted questions, and those are the ones that we are going to discuss. Okay, our next speaker is going to be Marc Gagne, who already has the microphone. We're going to pull up his presentation. And you have 15 minutes, and I'll give 12 minutes, and I'll give you a 3-minute warning.
Perfect, thank you. All right, thank you. Well, thank you for having me. This is sort of dovetailing a little bit on Dave Principi's flash talk today on the Trapezium Very Large Program. So these are the collaborators that have been working on this project. We have the MIT team that's been responsible really for extracting the data. I have my collaborators at the University of Notre Dame that have been doing the numerical modeling, and then we've been fitting the X-ray spectra at Westchester. Are we good? I won't step on that. All right. So this is a nice figure that we saw earlier, and the star in question is the one at the very center here, theta 1 Ori C. It's an 07 star. It's a main sequence star. It's a very young star, along with the rest of the pre-main sequence stars in the cluster. And I'm showing you this HST picture to give you an idea of the environment here. Theta 1 Ori C is right in the center. It provides about 90% of the ionizing photons for the entire Orion Nebula. And essentially, the Orion Nebula is a sort of evacuated hot bubble with a neutral lid. And that neutral lid is responsible for most of the photoelectric absorption that we see when we look at this object. Somebody pointed out that most massive stars are binaries, and this is obviously the case here. You have a spectroscopic binary in the center, which is composed of our main star, the magnetic one, 33 solar masses approximately, with about a 1 solar mass companion. And what's interesting about this companion is that it's only 10 stellar radii away from the O primary. And you'll see in our simulations that if I went to about 10R star, that star would be basically orbiting the outside of the simulation. So that's a rather rapid rotation of about, an orbital period of about 61 or 62 days. And then there is an early type companion, 12 solar masses, with an 11-year orbit, orbiting at about 17 AU. And when we do our simulations, we're really only going to be simulating this magnetic star at the center. This was the first magnetic O star ever discovered in the mid-1990s. We discovered some variable X-ray emission in 1997. And then in the Chandra data era, there have been observations going all the way back to 1999. And then if you include the data points for the from the VLP program, we now have 78 observations. There's the magnetic, so this is basically a rotating magnetosphere. And the thing to keep in mind here is that the magnetic axis is tilted with respect to the rotation axis, and now the rotation axis is tilted by about 45 degrees to us. And what that does is that it creates a situation where at different rotational periods, we're actually looking at the star magnetic pole down on the magnetic pole at X-ray maximum, and then at X-ray minimum, we're looking basically along this X-ray disk. And what we're going to be talking about today is diagnostics that we're trying to extract from the data, and then the synthetic diagnostics that we're trying to extract from the simulations and to compare those. So this is the X-ray spectrum. This is an outstanding spectrum. And one of the points I want to make today is that in terms of magnetic massive stars, this is going to be the best X-ray spectrum we get for one of these kinds of stars for a long, long time. And so the question is what can we extract in terms of meaningful diagnostics out of this data? And then how can that inform how we're going to model these in 3D with our MHD simulations? And so as you can see, we see everything from ionized nickel and iron 25. And I can run through these very quickly. So now we're looking at the spectrum all the way out to almost 10 angstroms here. And we start to cut off at about 20 angstroms. So past about 20 angstroms, the column density of hydrogen gets too bad. But I want to point out these line profiles. These line profiles are one of the things, the diagnostics that we really want to extract. And one of the things that we learned is that not only do you see these Lorentzian wings, these non-thermal wings on the long wavelength lines, but in fact, the signal to noise is so good that we actually need these void profiles to fit all of the lines, okay? And the point is that we want to see if the computer simulations are going to reproduce these line profiles. So we're trying to get as much as we can out of the data. We know, we suspected going into this that we would see phase variability in all of these diagnostics. And we have enough data now that we can actually phase bin the data. So we broke the data up into 11 phase bins, each with about the same signal to noise ratio, with a total of about 2.1 megaseconds. And then, of course, we analyzed the entire spectrum. We used APEC in ISIS. So this was all done with the ISIS program developed here by the MIT folks. And we basically used a 6T variable abundance APEC model to get the continuum. And our outlook was really to focus on modeling the lines. And the key point here is that it came down to actually analyzing the data two ways. The first way we did it is if I look at any one of these line profiles, or I can actually go ahead and show you some of the helium-like lines here. The first way would have been the typical way to do this in ISIS before, which would have been to essentially model a Gaussian, or in this case, a void profile for all of the important emission lines and to just model the continuum. We did that. We analyzed all the lines this way and we got decent results. But we also realized that we could do better if we actually just focused on the lines that we wanted to measure. So with the help of the MIT folks, we actually wrote some routines in ISIS where we were able to essentially model the entire spectrum minus the lines that we wanted to fit. So in this case, we would have modeled just the resonance line, just the intercombination doublet, just the forbidden line, and any bright lines that happen to be in the complex. And then all of the dielectronic recombination, all of the satellite lines, the weak satellite lines in the continuum essentially would have been taken care of in the model. And so essentially we modeled all of the lines. You've heard a couple of talks now on how we can use the F to I ratio to diagnose. In the case of coronal plasmas, we can use it to diagnose the electron density. But in the case of these massive stars, as Lydia and others were discussing, we can actually use it to essentially locate the plasma. So to give you an idea about the variability here, these are different things that we've modeled here. These are the R ratios and the G ratios for silicon-13. Up here at the top, we have the full width half maximum of the void profile in kilometers per second for the 11 phase bins. And then we have the flux in some of the hydrogen and helium-like lines. And quite surprisingly, actually, there's really not a lot of variation at all in the F to I ratios. And this is actually surprising because the simulations that we'd done before would have suggested that because of absorption in the disk, that we would have actually seen the apparent location of the X-rays to move around as we were looking at different viewing angles. So the fact that we don't see any variation in the F to I ratio, at least was surprising until we had a look at our latest simulations. And you'll see overall that all of the lines are basically doing the same thing. They're all varying approximately this way. So what we're going to learn about in later talks and what we've learned about earlier is that the diagnostic tool, this F ratio, really depends on this ultraviolet spectrum. So what you see here are the wavelengths of the ultraviolet radiation that pumps that level that leads to the lower forbidden line emission and then the stronger intergalvanation line emission. And what I want to point out actually is that if we use a T-Lusty model to model the spectrum and we use a power model, these are the Potsdam wind models, that the spectra are quite different. So what I'm going to show you here, so this is what we get if we use the T-Lusty model to model the F to I ratios, and this is in terms of the radial coordinate in stellar radii, and this is the inverse radial coordinate that Rico was talking about a moment ago. And I just want to illustrate one of the results that we found. So if we model that F to I ratio in terms of the T-Lusty model, the black is what we found in 2005, and these would be the error bars on the F to I ratios in 2005. The red represents our measurements now using this new ISIS model and the limits that we find. And in terms of this inverse coordinate, what this really is telling us is that at least for these two F to I ratios, the X-rays really are occurring at about 2 to 3 R star. And then for silicon 15, which is a little bit hotter, it's happening a little later. Let me tell you about the code very quickly. We have developed a code that uses geodesic meshes. They're not R theta phi meshes. This is really the only code that I know of that works with these geodesic meshes. And the entire reason we do that is that we want to eliminate the pole problem in our simulations. We have included a full energy equation in order to model the X-ray shocks. We basically use a tilted magnetic dipole, and we've included inverse Compton cooling in these models. And just to give you an idea of the kind of output that we get, so this is from a paper from a few years ago that Norbert was on that looked at the emission measure distribution. And what we see is that the magnetically confined wind shocks in theta 1 Ori C really are quite unique compared to other massive stars. And this is the emission measure distribution that we get from our simulations. I don't have a lot of time, so I'm just going to show you this one simulation here where we see the evolution of the plasma in our models. And what's interesting about these simulations is that they actually are quite stable. Other simulations that we've done using a different code, this is work that Asifullah and Stanowaki have been doing over time, show much more dynamic magnetosphere. And what we're seeing here is that in these simulations, both the density and the temperature are stabilizing here, but that the X-rays are produced mostly in these regions here, these regions of high density and high temperature, and otherwise what we're seeing is a pretty smooth wind. If we look in more detail though, right now we're having some problems with this energy equation because what we're seeing in fact is numerical heating out here. So normally you would expect the wind to be cool in these open field regions, but in fact what we're seeing is heating. So right now we're really trying to work on this problem to make sure that the numerical simulations are not introducing essentially numerical heating that isn't actually happening. But what is interesting about this simulation is that we really can understand both the X-ray emission and also the excess carbon-4 absorption that we see in the ultraviolet as really occurring really in this region. You can actually think of the X-rays as being like a torus around here, and that the X-ray dips that we see are really caused by not only occultation of the photosphere, but by absorption of this denser, cooler material within 1R star. So all of this we're quite confident with. What we need to work out here is what's going on out here. And I want to emphasize one thing about this entire process. The whole goal here is that, like I said earlier, we recognize that we're not going to get great data like this on other magnetic O stars for a long time. What we want to develop is a mechanism for modeling these systems, all of the magnetic O stars, where now we can vary the parameters according to the O star and know that the numerical model is actually going to make correct predictions for these stars. The other update I'll give you is that a handful of these magnetic stars actually are not magnetic dipoles, but are actually magnetic multipoles. So now we've built magnetic multipoles into this code so that we can model systems like Tausco and some of the others. All right, thank you.
I'm sorry for pushing you so hard. We are going to get one question in, but not everybody. You raised your hand first.
You go back to the plot you had of your F to I with phase. It was a little bit of a blip in a point or two. I was just wondering if instead of phase, if it were the viewing inclination of the magnetosphere, is that like related to whether those zones are occulted more or less? Is that connected?
Like I said, if we were to look at some of the earlier simulations that we had, we really would have expected a larger variation of those F to I ratios. I mean, at this point, yeah, so we do see some variability. No, so for the F to I ratios, we have not been able to investigate what the numerical models are predicting about the variability of the F to I ratios. That's something that'll probably be done this fall. And so
you can always ask more questions during the coffee breaks on Slack later. Unfortunately, I'll have to ask the next speaker to come up. Let's thank Marc again.
thank you.
I can keep that, but I want the other one. Our next speaker is Joy Nichols. You can slip this on or get it around your neck, whatever you prefer.
And just like this. So I'm well aware that I'm the only thing standing between you folks and a beer. So I will move on.
After you.
Oh, there is. Then I'll not rush. Okay. I want to talk about a survey of X-rays from massive stars observed with the Chandra HETG High Resolution grading. This is based on a paper that was recently accepted by Apjay Pradhan et al. And the team is listed here. Oops, sorry. The plan of the talk is a summary of the X-ray emission line profiles in massive stars, a description of our sample of stars and methods of data analysis, the line centroid and full width half max results, which are pretty fundamental, and then some comparisons full width half maximum with B infinity and effective temperature. And I'll describe some other uses of this database and summary and conclusions. So stellar winds of massive stars, you've heard quite a bit about, so I won't take long, but over their very brief life, relatively brief lifetimes, they lose a significant amount of their mass in the form of stellar winds, which are ejected. It's ejected in stellar winds. These stellar winds play a very important role in galaxy evolution. And it really in two ways. One is the interstellar medium is enriched. So each generation of star is more and more enriched. And over their lifetimes, they emit as much energy as a supernova explosion. And this is before they go supernova. So they're driving a lot of the dynamics and evolution of our galaxy, our neighbor galaxy. A key mechanism I had thought until I heard Lida talk was line deshadowing instability, which could explain the structure and clumping up in the wind, but apparently that's not necessarily sure at this point. Now, this is just a summary. You've seen this a couple times, but I'll go quickly. The point of this slide is that using the profile shapes and very detailed profile shapes, you can understand what type of wind conditions you're observing and quite a bit about the star. OB star line-driven winds, the shocks are embedded in the wind, the lines are broad and can be asymmetric and blue shifted. For the helium-like lines, the forbidden component is suppressed because of the UV flux destroying it. Binary systems, you have the wind-wind collision, and there you have symmetric lines or they can be double peaked. It's relatively hot and your forbidden line component will be strong. In the magnetically combined winds, you have narrow, unshifted component lines, and they are relatively hot with the suppressed forbidden lines. And then Wolf-Rayet stars with their very dense winds have broad lines, fin-shaped, and they have strong forbidden lines. So you can see that with very detailed study of the emission lines, you know quite a bit about the star. This is just a comparison of Chandra HETG and XMM. And the top is Wolf-Rayet WR6. And on the bottom is the XMM RGS WR6. And even your eye can see that that's not sufficient detail to see the components that I just described on the previous slide that you would need to know. Now, our sample of stars was not collected from a dedicated Chandra program. We took the data from the archive. So the spectra were selected, the stars were selected to meet the science goals of each individual proposer. And so that means it's diverse. It had to be included in our study, it had to be massive stars with HETG spectra that had sufficient signal to noise to do the detailed line profile analysis. Resulted in 37 O and Wolf-Rayet stars. We have 25 O stars, and importantly, we have a very good representation of the entire spectral range and the luminosity classes. So it's really, I think, useful for comparison. We have 9 early B stars and 3 Wolf-Rayet stars. There's 8 probable single stars, 27 known binaries, and 2 unknowns. We have 8 magnetic stars and magnetic star candidates, 3 gamma casts and analog stars, and 3 SIG-OB2 cluster members that seem to have anomalous characteristics. So to analyze the data, we reprocess them all essentially uniformly using Chow tools, scripted in the TGCat software system. You can download that from the TGCat website for processing data yourself as well. what we did, and this is on the right is a typical fit, it's theta O. We used a plasma model, multi-temperature plasma model, and fit the data that, so the black is the data and the cyan color is the model. We then determined the continuum by removing those emission lines from the model and evaluating it that way. But then we used Gaussian profiles to measure the lines to get the best fit. So the first thing we noticed was that after we determined some of our fundamental diagnostics, the line centroids and the line width, by doing a histogram, as you see on the right, of the line centroid offsets in velocity, 3 groups popped out to us. One group called zero offset was near zero velocity. This intermediate group at about minus 400 kilometers per second. And then that high velocity has a long tail. So we said, well, that's another group at higher negative velocity. So here are these 3 groups, and they're color-coded. Black is the low velocity. Intermediate is orange, or I thought it was orange. And high offset, that was the long tail, is blue. And you can see it loosely correlates with full width half max. If we plot full width half maximum against the line centroids, the low offset is a very tight group. The intermediate and higher, they're close, but distinct. So we notice the trend that there's the larger the negative offset, the larger the full width half max. This is the line profiles for iron 17 at 15 angstroms of the 3 groups. And you can see that the black group very nicely symmetrical about the 0. Whereas the second one, the orange, is very much broader. And the blue is shifted and broader. I'll skip that one. So then we plotted full width half maximum. This is for all our sample stars with good line measurements of these 3 lines, the iron 17 lines and the neon 10, against the infinity, and found a very tight correlation. Again, the colors are the same. The black are our first group. The blue and the orange mix a bit, but the correlation is incredibly tight for that. So then I have a couple others. I pulled a trick on you here. I switched colors because I was interested in seeing where do the magnetic stars lie? Where do the gamma cast stars lie? Where are the Wolf-Rayet stars? But it's full width half max against T effective, which is a proxy for optical spectral type. And again, we have a very nice, not tight, but not a bad correlation with basically spectral type, a full width half max. So that's an interesting result that would need some modeling and stellar parameter input. Other possible uses of the database, new observations could be compared to see trends. Our line width terminal wind velocity relationship could be used, for example, for cluster stars where you have high UV extinction and could not get terminal velocity from the UV. And finally, you could look for trends for different types of stars. What are the magnetic stars different than the whole class? Or we haven't looked at binaries; they could be different. So the summary is our database includes X-ray determined spectral parameters of 37 OB and Wolf-Rayet stars. And it also includes a gallery of X-ray luminosity versus wavelength plots. There's one for each star, and that puts them on an intercomparable format. The X-ray parameters are well described by optical spectral classification. And we have identified empirically 3 subgroups concerning centroid velocity, and they're generally correlated with terminal wind velocity. And finally, the full width half max of neon 10 and iron 17 at lambda greater than 12 angstroms is a reasonable proxy for terminal wind velocity. That's it.
Are there questions? Are there questions from people that are not Jan Uwe? Because he's asked a lot of questions. So if somebody else has one? No? Okay.
So how many questions have I asked? Tomorrow you tell me. Just about the iron 17 line, the one at 17.05, there's also one equally strong at 17.1. So it's actually a blend, and you actually get a higher full width maximum. If you go back 2 or 3 slides.
Yeah, I know what you're talking.
One more. Yeah, so the full width of maximum is higher for the iron 17 because the blend. So I just wonder, because it's 2 lines, and then you get a broader line than for the neon 10. Are they fit as separate lines?
They are fit
together.
Separation.
Okay, good. Thank you.
Another quick question? Okay, the last talk. I will thank the speaker again. The last talk is remote again. So please share your screen and start talking.
Okay, great. Thank you.
We can hear you.
Can you hear me?
We can.
Excellent. Thank you all for staying to the end of the afternoon session. I can see human beings in the audience there, so that's wonderful. I'm going to be talking to you about an X-ray spectral diagnostic of O-star wind mass loss rate. And this is a broadband spectral diagnostic. I'll be bringing up the line profile diagnostic that Joy, Lida, and Rico all talked about. And about half the talk is going to be about the diagnostic itself. And the other half is going to be about an application to that wonderful Zeta Pup legacy Chandra spectrum that several other speakers have told us about. Okay, so just a quick reminder, Zeta Pup is extremely luminous, drives a strong radiation-driven wind. The wind has a mass loss rate high enough that it should be at least partially optically thick to X-rays. It's got a strong soft X-ray spectrum, and the paradigm for X-ray production in effectively single O stars with strong winds is that there's a spatial distribution of hot plasma, not super hot, as we heard, maybe 12 million degrees at the max for Zeta Pup, thanks to nice work by Dave Hunemorter. So relatively modestly heated plasma, heated by shocks in the wind. As Lida nicely described, the line deshadowing instability is probably not the whole story, but it's probably part of the story. The wind is mostly cold, maybe 1% is X-ray emitting temperatures at any given point, and that cold component of the wind absorbs X-rays through photoelectric absorption, inner shell ionization of metals mostly. Okay. So the comment at the bottom of the last slide that if you want to understand what's going on in these winds, you've got to model the emission And you've also got to model the absorption is a key thing to keep in mind as I describe the context and the diagnostic to you. So on the left, you see a bunch of Chandra spectra, originally published by Joy and Nolan Walborn and Wayne Waldron about 15 years ago, and repeated here in Maurice Leutnegger's paper from 2010. And you can see that the earlier type stars with the stronger winds have harder spectra, and the later type stars, I know many of you are laughing that like a B0 star is considered a later type star, with weaker winds shows softer spectra. The middle column is a model, not fits, just a kind of universal model where the only free parameter is the mass loss rate of the star. And you can see that it does a pretty good job of reproducing this hardness trend with wind strength. So this trend you're seeing, the stars with the earlier spectral types and stronger winds have harder X-ray spectra, is a wind attenuation or wind absorption trend. Here's another example. This is our best fit model to the cycle 1 spectrum of Zeta Puppis, shown in black here. It's a compressed log plot. The strongest line is the 17 angstrom iron line. However, if you turn off the wind absorption in this model, you get the pink model, which has its strongest lines at longer wavelengths. The difference between these two spectra is huge. As you can see, about 90% of the soft X-rays generated by these wind shocks in Zeta Pup are absorbed by the wind, are attenuated, and only about 10% emerge and are observed by us. So we could turn this into a diagnostic of wind column density or mass loss rate. The little inset I just put up there just is to help you see, make quantitative what the wind opacity due to photoelectric absorption is like. Okay, so this idea that you could actually measure a mass loss rate using this broadband X-ray absorption was deployed about a decade ago on the star HD 93129, which is an early-O supergiant with a very strong wind. On the right-hand side of the slide, you can see the ACIS spectrum. We fit the grading spectrum, but we also fit the ACIS zeroth order spectrum. And a model with a lot of wind absorption fits the data very well. In the inset in that figure, you can see what happens when we turn the wind absorption off. So a huge amount of wind absorption, very wavelength or photon energy dependent. And you can see in the circled text from the abstract on the left part of the slide that the mass loss rate derived from the broadband modeling, which again, I haven't described in detail to you yet, is consistent with the mass loss rate derived from the X-ray line profile model that again, Rico mentioned and Joy and Lida referred to. Okay, so we can make a mass loss rate measurement. You can see in the table here that the mass loss rate from this broadband diagnostic is consistent with the mass loss rate from the X-ray line profile diagnostic. On the right-hand side, you see the differential emission measure distribution that we simultaneously derive while we're deriving the mass loss rate or the wind absorption. Okay, so now second part of the talk, the problem. So Zeta Pup has been analyzed by many different groups, and one exciting result from this newer Chandra observation in cycle 19 is a change in the X-ray line profiles. And this change is consistent with a wind column density change of 40%, a mass loss rate change or increase of 40% between cycle 1 and cycle 19. The X-ray line profiles definitely change. We published a moment analysis, a model independent analysis showing that they change. The interpretation is pretty straightforward, seems like a wind column density effect, but the surprise, the expectation that the wind column density or wind mass loss rate should not change on years timescale in Zeta Pup makes us want to investigate this further. So the question is, what does the broadband spectral diagnostic say about the wind column density and the mass loss rate when we compare the data taken in cycle 1 to the data taken more recently. Let me describe this model to you. So we make the differential emission measure emission component of the model using APEC, BV APEC, variable abundance, Gaussian broadened APEC, and we use 6 fixed temperatures on an equally spaced logarithmic grid. The plot of emissivities of each individual line seen in the spectrum down on the bottom part of this slide has 6 vertical lines on it, and those represent the 6 temperatures. So the free parameters of the emission component of this model are the 6 normalizations. You can almost think about these spectra. Each of these isothermal spectra I show you here are combined in a linear combination. You can think about them almost like basis spectra for our differential emission measure model. And then we also need an absorption component of this model. And we use the WinTabs model, which does an exact radiation transport integral rather than using an ISM-like absorption component that assumes that the light source is entirely behind the absorbing medium. This WinTabs model is necessary because the shock heated gas, remember, is spatially distributed throughout the wind. It's embedded in the absorbing part of the wind. The key parameter of this model is the column density we call sigma star, and it's directly proportional to the mass loss rate. Here's what the transmission as a function of wavelength for a best fit model looks like. You can see about 90% of the X-rays are absorbed at 20 angstroms, about 75% at 10 angstroms, and then the wind becomes optically thin down at the single digit angstrom region of the spectrum. This is a model, the color coding according to the temperature component, showing you multiple temperature components contribute to many lines. The left-hand model has no wind absorption. The right-hand model has modest wind absorption. Note that the lines are not only lower flux, but there's a wavelength dependent signature here. That's what enables us to simultaneously determine the DEM and the wind absorption column density. Here is the only spectrum I'm going to show you. I could show you more in the question and answer session if you'd like. And this is our fit to, yep, I see, thanks a lot. This is our fit to the cycle 1 Chandra spectrum of zeta pup, and I will show you some of the key parameters on following slides. I just want you to see that the fit is pretty good. Here's the key result. The column density parameter is higher in each of the 21 OBS IDs in cycle 19 than it is in the single OBS ID from cycle 1. The increase in the average column density, or weighted average, is about 35%, consistent with the 40% increase seen from the line profiles. We also see increases in the flux and the integrated emission measure between cycle 1 and cycle 19. So these 3 key properties that we derive from the model fitting are highly correlated. More on that in a minute. The shape of the DEM does not change very much within cycle 19 or between cycle 1 and cycle 19. The shape we find very consistent with what Hunemorter et al. Found in their 2020 paper on the same data. As a little bonus here, I want to show you that the N to O ratio, which is taken to be something like 60 times solar for zeta pup, quite extreme, is more like 20, we think, based on the Chandra spectrum. And that's also what we find when we fit the XMM spectrum, and that's what Anthony Hervé et al. Found in their very detailed modeling of this star's XMM spectrum. So you can also get these key N and O abundances out of this kind of work. So to summarize, this physics correlation between wind column density and mass loss rate, I think, has a pretty simple explanation. The amount of material in the wind increases, the amount available to emit X-rays increases. If you look in detail at the numbers, though, the efficiency of shock production must go up as well, because the emission measure goes up by about 8 times more than the column density goes up. Astrophysics implications. Why hasn't anybody else noticed this change before? Pretty interesting. I've got some points down here, but basically space photometry, very accurate. Ground-based photometry, not so good for such a bright star. difficult to calibrate space photometry from one mission to another. So I would argue that we really don't know what ZetaPup has been doing over the last couple of decades optically, and especially in the UV and in terms of its basic wind properties. And then finally, I just want to point out that there is this big XMM data set, and we are analyzing it in the same way. And here's the X-ray flux just in the restricted bandpass that corresponds to the Chandra gratings. And you can see that the X-ray flux is about as high during the cycle 19 observing period. This is XMM, remember, with just the Chandra observing time superimposed, than it is during most of the rest of the data set. So that's suggestive. And then here's the wind column density. The y-axis says mass loss rate based on some conversion factor assumptions, but that's the wind column density. You can see the highest column density period of the 20 years of XMM observations occurs around the time of Chandra cycle 19. So I think when we're done with this analysis, we will see that there's some additional information, valuable information from XMM. In conclusion, ZetaPup seems to surprisingly have a variable mass loss rate on timescales of years. And this can be seen both in X-ray line profiles and this broadband X-ray diagnostic that I've shown you. Thank you for your attention.
Thank you very much. I'm sorry to keep you 2 minutes above time, so I think we can have 1 or 2 or 3 questions if there are any. Or maybe people are just hungry and want to put their questions on Slack if there are any. Then I want to thank this and all speakers in this session again.